welcome to the fourth lecture of term for the module Space and Time. So today we're going to start to look at the theory of special relativity. So we sort of start examining more contemporary theories of physical theories of the nature of space-time. And this is kind of a step on from Galilean space-time, thinking about Galilean space-time. As I mentioned last week, there's a sense in which there are some continuities between Galilean space-time and Minkowski space-time, which, as we'll see, serves as a foundation for special relativity. But the notion that our actual physical space-time is a Minkowski space-time or something in the ballpark of that is much more widely accepted than that it's Galilean in structure. So yeah, as I say, Galilean space-time was a sort of useful stepping stone for getting to starting to think about Minkowski space-time. Okay, so what I'm going to do is I'm going to, as usual, follow the handout. So the handout, this handout is covers both week 4 and week 5. The topic's too big just to cover in a single week, really, because there are various notions that need to be introduced. We're going to cover about the first half of the handout, as you might imagine. So sections 1 through 6, if you've got a copy of the handouts in front of you, and then we'll come back to the rest in next week's lecture. Okay, so in thinking about special relativity, and we're going to come back to the notion of Minkowski space-time shortly, but to start to think about special relativity, it's important to think about the two key postulates that kind of form the core of the theory. And these key postulates are, on the one hand, the light postulate, and on the other hand, the relativity postulate. So the relativity postulate is very similar to the notion of Galilean invariance. So the relativity postulate, I'll start with that one, even though it's number 2 on the handout, says that the laws of nature are the same in all inertial frames of reference. So no experiment can reveal whether one is at rest or in uniform motion, or indeed exactly what the nature of that uniform motion is. So provided we're at constant velocity, the direction of that velocity, or if you like, the speed associated, can't be discerned by means of empirical experiment. So the sort of Galileo example of a person in a ship, in the hold of a ship, moving inertially, or the other examples that we used of someone in a plane or a train moving inertially, very similar. The idea is that empirically, provided those objects are genuinely moving inertially, not subject to accelerations, then you won't be able to tell by means of any experiment whether or what the nature of your inertial motion is. Okay, so pretty much straightforward, taken over from Galilean relativity, that one. The light postulate, on the other hand, is something quite new. In the light postulate, probably you're quite familiar with this, that the speed of light in a vacuum is a constant. Now, we can sort of empirically determine what that speed is, what the constant is, and it's roughly 300,000 kilometers a second, it turns out. So the speed of light in a vacuum is a constant, denoted c, which has the value of roughly 300,000 kilometers per second. But also, crucially, the light postulate says that this speed of light in a vacuum is independent of the motion, or indeed the acceleration, of the light source. So the light won't be somehow given a boost if the source of the light is in motion, or it won't be slowed down if the source of the light's in motion. So what this means is that regardless of one's reference frame, one will measure the speed of light emitted from the source to have the same value, namely c, because the motion of the source relative to your reference frame doesn't make a difference to the speed of light. So specifically, the light postulate says that neither absolute nor relative motion of the source makes a difference to the recorded speed of light. So from that, it follows that regardless of your regardless of your frame of reference, you're going to measure the speed of light to be the same, precisely because the motion of the source relative to your reference frame isn't going to make a difference to the behavior of light. So those two principles are kind of the core of special relativity, and some interesting and maybe surprising results follow from those core postulates, one of which is the so-called relativity of simultaneity. So to understand that notion, the notion of the relativity of simultaneity, we consider a thought experiment, a version of which was given by Einstein. So on this thought experiment, we're going to imagine there are two people involved. There's Alice and Bob. So Alice and Bob are the normal names given to observers in experiments in physics, thought experiments in physics. So Alice is on a train and sitting at the midpoint of the train. We don't need to worry about Alice for now. Bob, on the other hand, we'll return to her. Bob, on the other hand, is sitting next to the train track that the train's going to pass along. So Bob's sitting by the track and the train passes him at speed. Now, here's the thought experiment. Just as the midpoint of the train is passing Bob, he observes a pair of lightning bolts, rather improbably, striking the front and back of the train simultaneously. Now, okay, so consider Bob's situation. Bob can think that perfectly reasonably that since the midpoint of the train was passing him when the lightning bolts struck, then the light from each of the lightning bolts has travelled the same distance to get to him, namely half the train's length. Now, by the light postulate, the light from each bolt was travelling at the same speed towards him. And so it must be that the lightning bolts really genuinely struck the train simultaneously, as he seemed to observe. So we know that the speed of light is constant. I mean, I guess this, it's a but the light isn't traveling through a perfect vacuum, so there's a slight complication there. But presumably Bob can think, well, the mediums through which the light changed are basically the same, so it's just regular air that the light's traveling through in both directions, both from the front of the train, the back of the train. So he can reasonably think that the light from each travels at the same speed, and since it travels at the same distance and the flashes or the light reaches him at the same time, he can reason that the bolts struck the train at the same time. Okay, so that's Bob. Now consider Alice. So, as I said, Alice is sitting on the roof of the train at the midpoint. Now, from Bob's perspective, Alice is moving towards the light that's travelling from the bolt that hits the front of the train, and she's moving because from Bob's perspective, the train's in motion, right? So Alice is moving towards the light, travelling from the front of the train, and the light away from the light traveling from the back of the train once the bolt hits the back of the train. So because Alice is traveling towards it, Bob would expect Alice to observe the light from the front of the train before she observes the light from the back of the train, just because she's moving towards the source of towards the light, I should say, towards the light waves that are traveling from the front of the train and away from those that are traveling from the back of the train. And in fact, this is what she will observe. She'll observe the light from the front first, and the light from the back afterwards. Now, Alice is going to reason that the distances of the front and the back of the train from her are the same, right? So she knows she's sitting halfway down the train. And given the light postulate, she's going to reason that, well, if the lightning strikes had indeed been simultaneous, then the light from each would have reached her at the same time, because the speed of light is a constant, and the speed of the source or the acceleration of the source doesn't matter. So since it's a constant in both directions, both from the back of the train and the front of the train, and given that the back of the train and the front of the train are equidistant from her, she's going to reason that because she observes the light from the front of the train first, then actually the bolt strikes can't have been simultaneous, but rather the lightning bolt that hit the front of the train must have hit the front of the train before the lightning bolt that hit the back of the train. Okay, so she's going to think that the strike at the front occurred before the strike at the back. So that's interesting, because Bob regards them as simultaneous, and he anticipates the order that Alice will observe. Alice does indeed observe that order, and yet she reasons, again using the light postulate, that in fact the flash at the front of the train occurred prior to the flash at the back of the train. Now, note there's a sort of, we might sort of think, well, maybe Bob's right. Bob's right that they occurred simultaneously because he's the one that's at rest, and maybe there's something special about the resting reference frame or something like that. But notice, first of all, that from Alice's perspective, Bob's moving. So Alice sees Bob going past. So she's, from her perspective, she's stationary, whereas Bob's the one that's moving, right? So relative to her, Bob is moving from the front of the train to the rear of the train. Now, of course, we tend to think of the surface of the Earth as somehow a more privileged reference frame than the top of a train. So we'd ordinarily talk about, really it being the case that Alice is the one that's moving and Bob isn't. We might think there's something special about Bob's reference frame, therefore, and that maybe his judgment about the order of the lightning strikes is correct. However, this is faulty reasoning, according to special relativity, which privileges no reference frame. So there's no privileged reference frame relative to which we are entitled to make absolute verdicts about the ordering of events. Now, of course, you can sort of maybe sort of get into the special relativistic way of thinking a bit by pointing out that, actually, when we ordinarily think that Bob's at rest, we're just wrong about this, because the Earth itself is moving and the surface, so that there's rotation of the Earth. The Earth's orbiting the sun. The sun is itself moving relative to other galaxies and so on. Okay, so actually, there's nothing to privilege one perspective or one reference frame over the other. So when Bob reasons that the lightning strikes occurred simultaneously, there's nothing to privilege his judgment over Alice's judgment that in fact the lightning strike that hit the front of the train occurred prior to the lightning strike that hit the back of the train. Okay, so this is known, the sort of thought experiment illustrates the so-called relativity of simultaneity. So judgments of simultaneity will vary across reference frame. Something that Bob judges to be simultaneous, namely the two lightning strikes, is something that Alice, in her different reference frame, won't regard as simultaneous. So that's the respect in which simultaneity is relative to a reference frame. Okay, so the relativity of simultaneity is related to another phenomenon that is important in special relativity, and that's known as the phenomenon of length contraction. Okay, so what is length contraction? Well, Bob, of course, as we saw, regards the lightning strikes as having occurred simultaneously. Now, because of that, if we think about the char marks, so suppose that when the lightning strikes the front and the back of the train, it leaves some char marks by the side of the track or on the track. And so because Bob regards the lightning strikes as having occurred simultaneously, he's going to regard those char marks as measuring the train's length, right? So we've got, in his view, one char mark that corresponds to the location of the front of the train, another that corresponds to the location of the back of the train, and since the lightning strikes occurred simultaneously, he's going to say, well, look, the front char mark marks where the front of the train was at the same time as the back of the train was marked by the back char mark. So that's a legitimate, for Bob, measure of the length of the train. By contrast, Alice, of course, regards the strike at the front of the train as having occurred prior to the one at the rear of the train. So she's going to think that, well, actually, by the time the second strike occurred, the front of the train had moved on from where it was when the strike occurred at the front of the train. So we could reason about this from her perspective, more thoroughly from her perspective. So she's actually going to think that, well, the char mark from the first strike has moved backwards from the front of the train along the train. So that she's going to think, actually, Bob is underestimating the length of the train. So the train's longer than Bob thinks it is, because actually the char marks are closer together than the length of the train, because by the time the second char mark has occurred, the first char mark has moved towards the back of the train along the train. Okay. Now, notice that things are symmetric. Right, so suppose that, just to vary the thought experiment a bit, imagine there's in fact a twin lightning strike that Alice, rather than Bob, observes as simultaneous. Then she'll regard the train's length as corresponding to the distance between the char marks. But in Bob's reference frame, actually it's going to be that the strike at the back comes before the strike at the front. And he's going to think, well, by that time the front of the train's moved on, so the distance between the char marks is longer than the length of the train. Okay. So in general, we can sort of think of the method of measuring the length of an object that's moving relative to an inertial frame that one occupies by determining the position of its two ends in that frame at the same time. So for Bob, in the original case, the position of the two ends of the train at the same time are determined by the locations of or correspond to the locations of the char marks. And so relative to his inertial frame, we can measure the length of the train as the distance between the char marks. Okay. Now, so we've seen that Alice regards the train as longer than does Bob, because she thinks that the front of the train's moved on by the time the second lightning strike occurs. So Alice, of course, is the observer for whom the train, the object in question in this case, is at rest. So relative to Alice, the train is at rest, and she regards the train as longer than the observer, namely Bob, relative to whom the train's in motion. And this is a sort of general principle. So any observer for whom an object is at rest, such as the train is relative to Alice, is going to measure that object to be longer than any other observer. So any observer for whom that object's at motion, or relative to the reference frame of which that object's in motion. And so we've got, there's a sort of precise equation that we can give that, namely equation 1, that expresses the variation in measured length across reference frame. So L0 here is the measured length of the object in the reference frame according to which that object is stationary. So, for instance, in the Alice-Bob case, L0 would be the length of the train that Alice reckons the train to have, or measures the train as having. And if we want to calculate what length Bob will regard the train as having, well, that length will be shorter, and how much shorter is determined by equation 1. So from equation 1, just from the form of equation 1, we can see, so in other words, equation 1 measures length contraction, right? So the degree to which an object will appear shorter in a reference frame relative to which it's not at rest, compared to a reference frame at which it is at rest. So L0 giving the length that it's measured to have in the reference frame relative to which it is at rest. Now, so c is the speed of light, v is the relative velocity of the two frames, the one corresponding to the measurement L0 and the other corresponding to the measurement L. And so what equation 1 essentially is telling us is that where whether the relative velocity of the two frames is low relative to the speed of light, then length contraction is going to be minimal. But it becomes more and more significant as the relative velocities of the two objects approach the speed of light. So for a regular train, of course, regular trains here on Earth travel at only very small fractions of the speed of light. And so Alice and Bob's measurements of the length of the train are actually going to be very similar. But if we could imagine the train moving at some really significant fraction of the speed of light, then there's going to be much greater divergence between the measurements. Okay. Time dilation is kind of the flip side of length contraction in a sense that we'll see, right? So another thought experiment, and that it's not always easy, I think, to follow these thought experiments. So it really sort of bears a bit of reflection and careful consideration to really get what's going on in these thought experiments. So hopefully you'll have read about them already in some of the reading for this week. Maybe they'll be hopefully a bit reinforced at least by the lecture. Maybe you can go away again and either take your own time to sort of reflect on the examples as set out in the handout or in the reading, and sort of slowly sort of consolidate your understanding that way. At least for those of you who are not already well versed in special relativity. Okay, so time dilation. So let us suppose that Alice, sitting on top of the train, has a clock which she's placed at the front of her train, and she synchronizes it with a clock that she's placed at the back of the train. Now, we'll suppose Alice makes her way to the front of the train and flashes a torch towards the back of the train. So she records on the clock at the front of the train the time at which she flashes the torch. And we'll suppose that there's some mechanism that allows the rear clock to automatically record the time the light signal from the front of the train reaches it. Now, let's suppose that according to Alice's measurement, her original measurement of the length of the train is 100 meters long. And by comparing the time at which the light beam left the front of the train in this torch thought experiment and the time it was received by the back clock, she calculates that the beam has taken 1/300,000th of a second to traverse the 100 meters. In other words, she's getting a value for the speed of light that's the expected one. That's the sort of one that we empirically know the speed of light to have. I'm simplifying a bit, of course, because I'm supposing that just making the simplifying assumption that in this case, the light's traveling through at least something that approximates a vacuum. I mean, to be honest, if it came to a sort of real person on a train and the light's just traveling through Earth's atmosphere, at ground level, then that's not enough to make a significant to have a very significant influence on the speed of light versus its speed in a vacuum. So the assumption's a reasonable one. Okay. So we'll make a sort of exaggerating assumption now. So suppose, just to make this sort of the time dilation length contraction vivid, we'll make the rather implausible supposition that the train's travelling at half of the speed of light relative to Bob's reference frame. Then we can plug in the various values we have into equation 1, and we'll get the result that according to Bob's measurements, the train's actually only 87 meters long, right? So that gives us so we just plug in length according to Alice, the velocity, the relative velocity, which is half c, into this equation, and we'll derive the length according to Bob of the train. And the result is, in fact, that the length according to Bob's 87 meters, as opposed to Alice's measurement of 100 meters. So there's the phenomenon of length contraction. And, because I guess half the speed of light is quite a significant fraction of the speed of light, the length contraction's clearly non-negligible, right? So it's a whole 13 meters shorter as measured by Bob than as measured by Alice. Okay. All right, next supposition of this experiment, this thought experiment. Suppose that Bob has a clock positioned on the track at the point where Alice flashes the torch. And suppose that he also has one positioned on a different point in the track where the beam reaches the back of the train. Okay. Now, what Bob's going to calculate, so when he measures the difference in the reading of the clocks corresponding to these two events, namely the front clock where the light is flashed and the back clock at the point where the light is received, then Bob's going to calculate that this beam of light took, 1/344,828 seconds to traverse the two points. Right. So that is to say, he's going to get the expected value of the speed of light. Obviously, it's no longer 1/300,000 seconds because he doesn't reckon the train is 100 meters long, but he reckons it's only 87 meters long. So he's going to get a different recording for the length of time that it took the light to traverse the 2 points. Okay. So then you might think, well, Bob's measurement of the time elapsed differs from the measurements that Alice makes. So Alice has measured the light to take 1/300,000 seconds to traverse the train, whereas Bob has calculated the light to take only to take 1/344,000 and so on seconds to traverse the 2 points. So the question is, how can this be? Well, actually, from Bob's perspective, so the way Bob's going to understand it and the way it's going to make sense to Bob is that actually from Bob's perspective, Alice's clocks are running slow, right? Alice's clocks are running slow. And so that's why it seems to her that the light travels faster than it does for Bob, just because less time is elapsing on her clocks from Bob's perspective. So this is corresponds to the phenomenon of time dilation, and we'll come back a bit more rigorously to that next week. So specifically, again, we've got an equation that can allow us to predict the difference between time, the time elapsed as measured by Alice, and the time elapsed as measured by Bob, just as we have an equation for predicting the differences in their length measurements. We've got an equation, namely equation 2, for predicting the differences in recorded time according to the two reference frames. So that's given by equation 2, and as before, T0 is going to be the measurement of time in Alice's reference frame, and T is going to be the measurement of time for the same event, or same process, the light traveling from the front of the train to the back of the train, in Bob's reference frame. And basically what we find, according to this equation, is that the faster that the relative velocity of the two reference frames is, if you like, the faster that the train is traveling, according to Bob's reference frame, the more time dilation there is. That is to say, the slower it's going to appear to Bob that Alice's clocks are running. Now, what you may be able to tell already from these two equations is that length contraction and time dilation offset one another. So this is the sense, I suppose, in which they're kind of two sides of a coin, or as I sort of suggested at the beginning. And it's this offset that allows the explanation of why, although lengths and times in one frame are judged to be different from in another frame, nevertheless, both frames, and indeed all frames, are going to be able to agree on what the speed of light is because of this offset between time dilation and length contraction. So again, this is just a sort of introduction to this way of thinking. We'll have much more to say about this, especially next week, and try to make it a little bit more precise. Okay. So, I mean, I guess this sort of paragraph in the handout here is something I've already really covered. So you might be tempted to say, well, Bob's observation, not Alice's, is the correct one, since Alice is the one who's really moving, while Bob's really stationary. But actually, as I've said, special relativity doesn't in fact privilege any frame of reference, and in any case, ordinary intuitive judgments of who's really moving, who's really stationary, are dodgy, because in fact, contrary to how we ordinarily think, the surface of the Earth is moving, and so on. Okay, so with that sort of background, I mean, it's a sort of very rough overview of some of the key points of special relativity, and as I say, we're going to sort of dive in a bit more detail, especially next week, but to some extent in the remainder of this lecture. But we're in a position now where we can introduce the space-time framework that's can be considered the background or a foundation for special relativistic thinking. And remember, of course, this ultimately is a course about the nature of space and time, so this should be of interest to us. So specifically, special relativity is formulated against the backdrop of so-called Minkowski space-time. So as the name suggests, we're taking into account 4 dimensions, so the 3 spatial dimensions and a time dimension. Now, having said that, I should sort of row back a little bit in that the distinction between time, the temporal dimension, and the spatial dimension in some ways isn't quite as sharp as we might have thought it was when we were thinking about Galilean space-time and indeed Newtonian space-time. And that's related to this relativity of simultaneity. So essentially what this means is that there's no uniquely correct way of, if you like, so if you thought of space-time as a kind of 4-dimensional block, then there's no unique way of sort of cutting it into spaces, purely spatial segments, so 3-dimensional purely spatial segments, or in other words, taking time slices. That's another way of describing this. In other words, there's no, sort of to put it slightly more technically, there's no uniquely correct way of foliating space-time into sets of simultaneous points, that is, points that according to all of which it's the same time. So the distinction between time and space becomes a little bit more blurred than it does in Galilean or Newtonian space-time. So we'll see this in more detail as we go through. So to get a sense of the structure of Minkowski space-time, it's going to help to kind of start pretty slowly and simplify a lot, right? So firstly, we're going to consider a 2-dimensional space, and indeed a 2-dimensional Euclidean space, and then we're going to sort of build up towards 4-dimensional Euclidean space, and then finally we're going to talk about the distinction between Euclidean space and Minkowski space-time. Okay. So if you think of 2-dimensional Euclidean space, and so what we're going to start by thinking about is the notion of a straight line in 2-dimensional Euclidean space, and straight lines are going to, a straight line is going to be a certain set of points defined by certain coordinates known as Cartesian coordinates. So one way of sort of thinking about coordinates is we'll let this lowercase s be a variable that can take any real number as a value, and we're going to suppose that a, b, c, and d each correspond to real numbers. So one way of thinking about coordinates, Cartesian coordinates in a 2-dimensional Euclidean space, is that they could be given by this formula here. So s, the product of s and a plus b gives you the x coordinate, and the product of s and c plus d gives you the y coordinate. Okay. Now, suppose that a is 0 and that c is also 0, then these first terms are just going to be 0. So actually, what we are left with is not really it is a set of points, but it's a singleton set, a set of points with only one member, namely the points given by the coordinates BC. Okay. Now, if it also happens that B is 0 and C is 0, then the point in question is the origin point with the coordinates 0, 0. Now, where either A or C isn't equal to 0, then the set of points with these coordinates is going to form a straight line. So, for instance, suppose that we're going to let A take value 1 and set B, C, and D equal to 0, then that's just going to give us our x-axis. So specifically, for any real number s, this formula s multiplied by a plus b, s multiplied by c plus d, returns, so remember that b, c, and d are all 0, so the second term is going to be 0, so our y coordinate is going to be 0. The x coordinate is always just going to be equal to the value of s. And since s ranges over all the real numbers, this just gives us our continuous x-axis. And likewise, where we let c be equal to 1 and a, b, and d be equal to 0, then this formula gives us our y-axis. But basically, any straight line can just be defined via varying choices of a, b, c, and d. So I've illustrated some in figure 1. So if you can, you're in your own time, sort of satisfy yourself, of how these lines are defined in terms of this formula. And specifically, I've given the values for a, b, c, and d that when combined with this formula yield the lines in question. Okay. So that's something hopefully fairly straightforward about the notion of a straight line in Euclidean two-dimensional space. Now, when it comes to three-dimensional Euclidean space, so I suppose if you're Galileo, then you're thinking of actual physical space as being a three-dimensional Euclidean space. So, in a sense, slightly more realistic when we're interested in physical space. Things are very similar. It's just that we need 3 coordinates to pick out a point. So, in two-dimensional space, you just need 2 coordinates to pick out points. Whereas in 3-dimensional space, you need 3 coordinates, an x coordinate, a y coordinate, and a z coordinate. Okay, and so that the sort of coordinate formula then just becomes this one on the handout. And so where at least one of A, C, and E is non-zero, then we get a line rather than a point. Yeah, actually, sorry, I've written the wrong thing here. So this should say in 4-dimensional Euclidean space-time, then a straight line is given by the sort of slightly more complex formula that just reflects the fact that we need 4 coordinates to give to give a space-time point in 4 dimensions. So that should be 4-dimensional Euclidean. So if A, C, E, and G in this case are all 0, then we pick out a point rather than a line. That is a single coordinate rather than a set of coordinates. But if at least one of A, C, E, and G is non-zero, then we get a line rather than a point. Okay. Okay, so hopefully that seems reasonably straightforward. If it isn't, hopefully reflection on just so if you have another read through the handout and just reflect upon how, for instance, these straight lines are defined from the formula that we have for these values of A, B, C, and D, then things will be clear enough. Okay, so all right, so we've said something about how we define straight lines in Euclidean space. We considered the example of two-dimensional Euclidean space, three-dimensional Euclidean space, and four-dimensional Euclidean space. They're sort of not much different, only each time we need an extra coordinate. One thing I should say is that four-dimensional Euclidean space, it's not really proper to think about that as corresponding to something like Newtonian or Galilean space-time, because on those theories, there's no supposition that the fourth dimension behaves like the three spatial dimensions. So in particular, there's no supposition that the whole four-dimensional structure is going to itself be Euclidean. All that's assumed is that each, if you like, three-dimensional segment of it or three-dimensional foliation of it is going to behave in a Euclidean way. So actually a four-dimensional Euclidean. So yeah, sorry, the mistake on the handout. I just must have had I must have had a Minkowski spacetime on the brain. So that should actually say four-dimensional Euclidean space. Although we'll see in a minute that things are going to work quite similarly when it comes to Minkowski spacetime. So actually, when we talk about four-dimensional Euclidean space, this should really be thought of as a sort of hypothetical scenario in which space itself has a fourth dimension. Okay, so so we've said something about lines, but it's also interesting to say something about the distance between points in a Euclidean space. And we can start simply with the two-dimensional case. And the distance between 2 points, A and B, in that space, in a two-dimensional Euclidean space, is given by the formula equation 3. Now, this needs a bit of explaining. So here, x and y are just functions that return the x coordinate and the y coordinate, respectively, of the point that they take as an argument. So x of a is a function that's just going to return the x coordinates of point A. X of b is going to return the x coordinate of point B. Likewise, y of a gives the y coordinate of point A, and y of b gives the y coordinate of point B. So, in other words, what equation 3 says is that the distance between A and B in a two-dimensional Euclidean space is given as the square root of the sum of the square of the x distance plus the square of the y distance. So this is illustrated. We can think about how points A and B being these 2 points illustrated that lie on the orange line in figure 1. And the x distance between A and B is actually given by the line from A to C. That's the distance between A and B along the x-axis. And then the y distance between A and B is given by the length of the line from C to B. That just gives the y distance between the point A and point B. So, I guess for anyone with much background in geometry, this is going to be all fairly obvious. But just for the sake of those who maybe don't, um, uh, so you might ask, well, why do we have this sort of fancy formula that gives the distance between A and B in terms of the x distance between the two and the y distance between the two? In particular, why are we squaring the x distance and squaring the y distance and then taking a square root? Well, basically, this is just an application of Pythagoras' theorem. So you can see that ACB is a triangle. It defines a triangle, and specifically a right-angled triangle. So this is actually just an application of Pythagoras' theorem, because what we want to know is we want to know the distance from A to B, and Pythagoras' theorem tells us that when we have a right-angled triangle, the square of the AB distance is equal to the sum of the square of the AC distance plus the square of the CB distance. So we can work out, as I say, the square of the AB distance by just summing together the squares of the AC distance and the AB distance. But actually what we want to know is the AB distance, not the square of the AB distance. So we just take a square root. So that's all that's going on in equation 3. And we can generalize this to a three-dimensional Euclidean space. And so here we have not only an x and a y-axis, but a z-axis. And so basically we've got to take into account the z distance between the points as well as the x and the y distances. And the formula is just a generalization of equation 3. So we want the square root of the sum of the squared x, y, and z distances. And that gives us the distance from point A to point B. And of course, we can move up the dimensions. So 4-dimensional Euclidean space, maybe we've got coordinates w, x, y, and z. And the formula is, again, just going to generalize. So the distance between A and B in 4-dimensional Euclidean space is just the square root of the sum of the squared w, x, y, and z distances, right? I guess I wrote that a bit, just messed up the notation a bit. Okay, right. So now finally Minkowski's spacetime. So Minkowski's spacetime is 4-dimensional. And things are quite, in some senses, things are quite like 4-dimensional Euclidean space, in that, again, we're going to need 4 coordinates to specify a point in this 4-dimensional space, or strictly a space-time. It's not a pure, it's a space in the geometric sense, but physically it corresponds to a space-time. Now, by convention, one of the coordinates in Minkowski's space-time is labeled t. And so, this suggests time, right? So I've sort of cautioned against the idea that there's a very straightforward separation between time and space in special relativity and in Minkowski space-time. But the t-dimension, the labeling is supposed to indicate that this is kind of like, at least like a time dimension, like the sort of time dimension that you might imagine in Euclidean or Galilean space-time. So there's a reason why it's labeled t, whereas the spatial dimensions get the labels x, y, and z. Okay, so we don't really speak, normally use the terminology of distance exactly when we're talking about when we're comparing points in Minkowski's space-time. So you can talk about distance if you want, but sort of more formally, people talk about the space-time interval rather than the space-time distance. Interval is, I guess, short for invariant relativistic interval. It's invariant because it's something that doesn't vary across reference frames. And it's given by so this sort of, if you like, distance measure, or more properly interval measure, is given by equation 6 on the handouts. So note that it's denoted with an I, so interval AB rather than distance AB. So space-time interval. And there's a sense in which the equation looks a bit, in some respects, like equation 5, which is just the distance between 2 points in Euclidean space. But there are also some noticeable differences, right? Well, what's the analogy is that, again, interval in Minkowski space-time. Sorry about that. So the difference is that, let me just get this back up, is that interval in Minkowski space-time, just like distance in Euclidean space-time, is given as a function of 4 coordinates, or the differences in 4 coordinates of the points A and B. In this case, obviously the t coordinate, we use t for one of the coordinates rather than w. Now, and another, I guess, common feature is that we're taking a square root in each case, which is a sort of generalization of the Pythagorean principle. But one thing, well, there are a couple of very important differences. And one is the presence of the minus rather than the plus after the first term in the expression. So in equation 6, we have the distance along, or the sum of the squared distances along 3 dimensions being actually subtracted from the squared distance along the 4th dimension, rather than added as it is in equation 5. So that we'll come back to why that is and what that corresponds to. But obviously, already looks like it might be an interesting difference. The other point to note is that we have this term c squared, or the speed of light squared, in the expression for the interval measure, whereas nothing like that appears in the expression for the distance measure in 4-dimensional Euclidean space. Okay, now arguably there's a sense in which maybe the c squared we shouldn't focus too much on, at least for now. It is important, but we don't have to focus on it too much just yet, while exploring some of the properties of this this interval measure. Now, Maudlin himself, as you might have seen in the reading, actually omits c squared from the equation, and basically this is okay. So there's a bit of a long story here, but he's taking the speed of light to be the unit, so that spatial distances are measured as fractions of the speed of light. In other words, they're measured in light seconds. And so that means that, provided we're using c as our unit, then this can drop out of the equation. and we can focus on the other terms. So we'll actually be using Magdalen's formulation going forwards just for simplicity. But we'll return to this point about the unit of measurement being light seconds in a little while. Okay. So I've covered this. So in four-dimensional Euclidean space, the sum of the squared distances between A and B and their x, y, and z coordinates. I should have added, is added to that in the w coordinate. But by contrast, in Minkowski space-time, we subtract the sum of the differences in their x, y, and z coordinates from the difference in their, or the square difference in their t coordinates. So that's a disanalogy. What we'll see below is that another interesting thing that we'll see below is that, as I've already suggested, observers in all reference frames are going to agree about the interval between events, and that's why it's known as an invariant interval, invariant relativistic interval. It's invariant in the sense of it doesn't vary across reference frames. So all observers in all reference frames are going to agree about the space-time interval between events. But having said that, they're going to disagree about the spatial and temporal distances between the two. So in the way that we saw that Alice and Bob disagree about the spatial and temporal distances between the lightning bolts impacts, but they will, it turns out, agree about the space-time interval between those two events. So what's going on essentially is something that we've alluded to before when we talk about time dilation and length contraction, is that difference in spatial measurements across frames are exactly offset by differences in temporal measurements, so that the interval value remains the same. Okay. Now, okay, so one interesting point about, so further interesting point about the interval measure, and we'll come back to this shortly, is that actually the interval measure is going to take 0 in some cases, even when A and B are distinct points. So if A and B are distinct points in a Euclidean space, that is to say, if then A and B are not the same point, then their Euclidean distance is always going to differ by some positive amount. But the corresponding point doesn't hold true of Minkowski space-time, so A and B can be different space-time points, and nevertheless have a non-zero interval. I should say, nevertheless have a zero interval between them, or if you like, zero distance between them. Maybe this is one reason why distance is a little bit of a naughty word here, and interval's the proper word. So we can roughly see that here just by noting that what one term is subtracted from another term. So you can imagine if the first term is the same size as the second term, then the result is going to be a zero distance. And it turns out that that is possible even where A and B are distinct in Minkowski space-time. Okay. Okay. So let's think now about well, I mean, I guess sort of another thing we'll come back to, but might be worth mentioning at this stage, is that when it comes to Euclidean space of any dimension, you can choose different Cartesian coordinate systems. So you just need to, you basically need to choose an origin point, but that origin point is arbitrary, and also orient the axes, and provided the axes are at right angles to one another, then you can choose any orientation for the axes that you like. And so actually there are infinitely many different Cartesian coordinate systems that you could choose for Cartesian space. And likewise, there are infinitely many coordinate systems that you can choose for Minkowski space-time that differ in origin, choice of origin, and orientation of the axes. Now, I suppose sort of, although there's that much conventionality, what's going to be of interest is that some quantities are invariant across choices of axes, of choices of coordinate systems. So distance is an invariant, is something that's invariant across choices of Cartesian coordinate system in a Euclidean space. And likewise, interval is something that's invariant across choices of Lorenz coordinate systems in a Minkowski spacetime. But again, that's something we'll come back to. Okay, so I think the sort of final thing that I want to do this week, and as I say, we'll carry on with the topic of special relativity and Minkowski spacetime next week, is to introduce the notion of a Minkowski diagram. So a Minkowski diagram is a representation of Minkowski spacetime. So the idea is we're going to take this four-dimensional spacetime that reality is supposed to comprise and provide a representation of it. Specifically, we want to represent it when we're kind of trying to sort of illustrate what's going on in special relativity in 2 or 3 dimensions. I say 2 or 3 dimensions because actually normally what we have is a 2-dimensional bit of paper or a 2-dimensional whiteboard or something similar. But we can kind of give the illusion of a 3rd dimension even when a representation is on a 2-dimensional bit of paper by making it appear as though there's another axis, a 3rd axis coming out from the page. And that's essentially what we do normally when drawing Minkowski spacetime diagrams. Okay, so basically we've still got a problem because even if we could give the impression of 3 dimensions, we can't readily give the impression of 4 dimensions, despite the fact that Minkowski spacetime is actually 4-dimensional. So what we're going to do is we're going to sort of suppress one of the spatial dimensions. So if you like, we'll represent x and y as spatial dimensions, but we'll kind of suppress the z axis. I suppose the reasoning being that let's keep t because t is kind of more interesting. Z is just another spatial dimension. So we're not going to misrepresent as badly if we suppress z as we might do if we suppress t. So by convention, the t dimension is represented vertically in the diagram. And an example of a Minkowski spacetime diagram is figure 2. So forget about the orange cones for now. So we've got the t is the vertical axis, and we've got, so this roughly speaking is the time dimension, and then we've got 2 spatial dimensions represented corresponding to the x-axis and the y-axis, which we try to give the impression of this coming out of the page at right angles to the t and the x-axis. But there's no room to include a further spatial dimension in our representation, so we suppress that. Okay. Okay, so as I said, the sort of counterpart of Cartesian coordinates in Minkowski space-time are Lorenz coordinates. And when we are providing a coordinate system, again, we've got to choose an origin point. So the origin is in the representation is where the axes intersect, and that, as you would expect, if we give the full four-dimensional coordinates, by convention, the coordinates of the origin are just 0, 0, 0, 0. So 0t, 0x, 0y, 0z. So remember that we're using the sort of Maudlin version of the interval measure. There's actually a bunch of ways in which you can state the interval measure. We're using the Maudlin one that drops reference to the constant c, the speed of light, because the distances are taken to be measured in terms of a unit of speed of light, so light seconds. That makes that legitimate, but it's something we'll come back to. Now, so we can tell that basically, let's suppose that B is the origin point, so it has these coordinates 0, 0, 0, 0. Then one thing of interest is under what circumstances a space-time point, or sometimes referred to as an event, when people talk about space-time events, they mean points rather than events in the everyday sense. And it's a bit confusing because if they talk about an event A in space-time, they mean a point, whereas in ordinary language, by an event, we mean something like a football match or something, which isn't a point in space-time. And also in probability theory, event has a third meaning again. So don't get confused by this when people talk about events in space-time, unless the context suggests otherwise. What they have in mind is a point. So point A in space-time is going to have zero interval from the origin if the t distance of A from the origin point is equal to or I should say the squared t distance from the origin point is equal to the sum of the squared x, y, and z distances from the origin point. So basically, we've sort of plugged here in equation 4. What I've done is I've plugged in the t, x, y, and so I've taken equation. I don't know why I've gone back to. I've misnumbered the equation, so I don't know why I've gone back to equation 4. But essentially, what I've done is I've taken the equation 6, which is the general formula. As I say, we've just suppressed c for the time being. Taken equation 6, and we're interested in this point A, which differs from the origin point. We're taking B to be the origin point, and because B is the origin point, we know it's a coordinates 0, 0, 0, 0. So we can just plug in zeros for the t axis value of point B, and likewise for the x, y, and z axis values of the point B. So I've just plugged in the zeros into equation 4, and so the whole thing simplifies. So the interval of point A from the origin is just given as the square root of the squared of its t value or t coordinates with the sum of the squares of the x, y, and z coordinates of A subtracted from that. Now, we can simplify again because only 0 has square root 0, so we know that if this expression has value 0, then so must the expression given as equation 5. So in other words, in order for the point A to have 0 interval from the origin of our space-time diagram, it must be that the square of the t-coordinate of A is equal to the sum of the squares of the spatial coordinates. So if you like, the square of A's time coordinate must be equal to the sum of the squares of its spatial coordinates. That's the second term. So in other words, the first term must be equal to the second term, so that when you subtract the second term from the first term, you get a value of 0 interval. Now we can plot the set of points that satisfy this equality, in other words, that have 0 interval from the origin point of our Lorenz coordinate system on a Minkowski space-time diagram. And the result of doing so is a double cone structure, where, if you like, the tip of each cone is the origin point. So that's what's illustrated in figure 2. I guess depending on the amount of maths or geometry you've done, this will either be totally obvious to you or perhaps not at all obvious that the result should be this double cone structure. I've provided, so if it's not obvious to you, then just trust me, this is what happens for the moment. I've provided a kind of intuitive explanation of why this is what the structure we get when we plot the set of points of 0 interval from the origin on our Minkowski space-time diagram. So the intuitive explanation is just provided on the handout here. So I'll leave you to read that through at your leisure if you want to. Now, what's interesting is that the trajectory, so this sort of double cone structure corresponds to something physically real. So the set of points that have 0 interval from the origin corresponds to something physically real, which is the trajectory of light in a vacuum, right? So if we take our origin point, then the cone structure, so take the cone that goes vertically up from the origin, that describes the set of all points that could be reached from our origin point by a light signal, provided that the light was traveling at the rate that it does in a vacuum. In other words, provided the light was traveling through a vacuum is what I should say. On the other hand, the lower cone, the cone that sort of, if you like, emanates vertically downward from our origin point, is sort of the flip side of this. It's the set of all points such that if you emitted a light signal from any of those points, then the light would reach the origin point, provided the light was traveling through a vacuum. So, corresponding to this, the cone that goes sort of upwards, if you like, from the origin point is known as the future light cone of the origin point, whereas the cone that goes, so the set of points that the future light cone is a set of points that could be reached from the origin point via a light signal, whereas the backward light cone, the one going vertically down, or if you like, past light cone, is a set of space-time points that could reach our origin point via a light signal, or in other words, you could signal from those space-time points to the origin using a torch, for instance. provided there was only vacuum between you and the recipient of the signal. Okay. So so this sort of the zero interval points correspond to something physically real. Light in a vacuum traverses the zero interval points, and that's not, that in a sense that is no accident, right? And that's because we're taking light to be the unit of measurement, so that light. So we're measuring distances in light seconds. So obviously, light travels at 1 light second per second. That's just sort of the definition of a light second. It's the distance that light travels in a second. So obviously, light itself travels at 1 light second per second, or at least light in a vacuum does. So there's a sense in which this is not accident. This is not like a big puzzling coincidence at all that light traverses this zero interval. Although what is interesting and what's not just trivial is that this zero interval, besides being the trajectory traversed by light in a vacuum, also sort of has some physically interesting properties, and we'll return to those mostly next week when we talk about the twins paradox. Okay, so let's see. Okay, so we've got a double cone structure. Actually, the fact that it looks like a cone is, in a way, an artifact of our diagram, and in particular, an artifact of the fact that Minkowski space-time diagrams are representing 4 dimensions using 3 dimensions, or 2 dimensions plus another pretend or sort of the illusion of a third dimension. So actually, in 3-dimensional space, of course, or 4-dimensional space-time, the light emitted from a point is going to expand in a sphere in space from the point at which it's emitted. It's just that when we try to represent an expanding sphere using 2 spatial dimensions and 1 temporal dimension, then the result is a conical structure like the one that we see. Okay, so a lot of setup this week, a lot of sort of technical setup. We'll get to some of the sort of more interesting implications of all this next week, but there are still a few I guess sort of background points that are worth noting before I end. So in Minkowski space-time, there are interesting notions, technical notions of light-like separation, space-like separation, and time-like separation, and we'll get a bit more of an intuitive sense of why they're called these things as we go along. But I mean, light-like separation maybe is sort of intuitive enough. So if any point on either of the cones is said to be light-like separated from the origin point, so it's one that could reach or be reached by the origin point or from the origin point by a signal traveling at the speed of light in a vacuum. So we call them light-like separated. Events that fall inside of the past light cone or the backward light cone, or inside of the forward light cone or future light cone, are known as time-like separated from the origin point. So that's just the term we use for those. They're time-like separated. Points that specifically lie time-like separated in the backward light cone, in the past light cone, are known as points that lie in the absolute past of the origin point. And there's a reason for this, that basically all reference frames are going to agree that any point that lies in the absolute past of, or within the backward light cone of the origin point, is indeed in the past of the origin point. Correspondingly, anything that lies in the interior of the future light cone is known as the absolute future of the origin point. And that's because all frames agree that such points lie in the future of the origin point. The rest of the points that lie neither on the surface of the light cones nor inside the light cones, are said to be known as the points that are in the absolute elsewhere of the origin point. Right, so they're known as the absolute elsewhere of the origin point, or sometimes they're said to be space-like as opposed to time-like and light-like. So space-like separated from the origin point. Note, by the way, we've done everything with respect to a particular origin point, but this generalizes to any point you might pick in space-time. So any point in space-time is going to correspond to a light cone structure, a set of points which it can reach or be reached by a signal traveling at the speed of light. And that just corresponds to the fact that the choice of origin point is perfectly arbitrary. We can choose any point in space-time as our origin point when we're providing a Lorenz coordinate system. Okay. All right, good. So now, I mean, we're going to come back to much of this next week. One thing that's interesting is that if 2 points are space-like separated, then there's always a reference frame in which they're simultaneous. They're going to be simultaneous in some reference frames, or in one reference frame, but not in others. Whereas if they're time-like separated, then they're simultaneous in no reference frames. And indeed, all reference frames will agree about whether the event's in the past or the future of a particular event. Okay, but we'll come back to that, as I say. Just two final points before we finish for this week, and we'll pick up on this next week. The first is the so-called limiting role of the light cone. So this is something that probably everyone's familiar with, the idea that, and this is a slightly dodgy way of putting it, but the sort of slogan is nothing travels faster than the speed of light in a vacuum. So slightly more precisely, we can say that the world line of an object that goes through some space-time point P never goes outside of the light cones of P. So in other words, you can't. So I mean, this corresponds to the idea that if an ordinary object, certainly an object with mass, can't go outside of the light cone of any point that it travels through. So specifically, as the velocity of that object approaches that of light, the velocity of light in a vacuum, then the amount of energy needed to move it goes to infinity, which means that no material body can ever be accelerated up to the speed of light. No massive object can be accelerated to the speed of light So photons are massless, and obviously they, being light, they move at the speed of light, and that's only achievable because they're massless. And then a final sort of point to note in this context is the relativistic law of inertia, which says that the trajectory of any physical entity that's subject to no external influences is a straight line in Minkowski spacetime. So this, of course, should be reminiscent of Newton's first law, which is that any massive object that's not subject to any forces will traverse a straight line, right? In Newtonian mechanics, we're assuming the straight line is through three-dimensional Euclidean space, but there's this similar principle in special relativity, that any physical entity that's not subject to external influences will traverse a straight line in Minkowski spacetime. So there's significant continuity, as well as the differences between Minkowski spacetime and special relativity and theories that have gone before. Okay, so I've already gone on for too long this week, and so we've done a lot of the sort of setup of Minkowski spacetime and special relativity, and we're going to come back to discussing more of the interesting implications and maybe philosophical implications in next week's lecture. But that's it for now. So thank you very much for bearing with me through what's quite a lot of fairly technical material, and I will speak to you all next week. Bye.